you're going to hear kind of a mathematical viewpoint on water in the river. This was work from myself, Shailene Chavadia, who's in the audience here. Thanks for coming. She can field all your questions, as well as Adrian Woodson from the South Central Climate Adaptation Science Center. That's the primary funding body of this work. My background, sorry, I'm not used to speaking with the microphone. I'm used to being stuck in a lab, mathematical modeling. My background is snow hydrology, and more specific than that, it's looking at the interactions between forests and snow, which is very much the origin story of where the water comes from as it rolls down. What is that sound?
Mexico jumping mountains.
So how does this clicker work? What's going on?
Press the right hand one. Oh, push on. Should be the right hand one.
Okay, there you go. Yeah, I'll just let you. There we go. Okay, it worked then. I just need to get a little closer. You all just saw this from Josh, I believe. Let's first define what the Upper Rio Grande Basin is. Outlined in white here, so from the headwaters from Creede, Colorado, down to Fort Quitman, Texas, about 32,000 square miles. I need to highlight this before we talk about climate projections, et cetera. 75% of the stream flow, you all are probably familiar with this, originates from snowpack and from these primarily small areas in red relative to the total basin size, and primarily as a little sideline from forests to headwaters. You know this as well. The river is highly managed, and despite withdrawing water from the Colorado River Basin, so what is that? From Navajo, Little Navajo, the Cromo River, down the Chama into the Rio Grande. The water sometimes dries up. Here is all of my colleagues' least favorite picture, but my favorite picture, because I kind of think it gives an overall viewpoint of what's going on in the basin with these water-generating high alpine watersheds above. And the river here with the raging 10 CFS. This is the state line around Lobatos, USGS gauge. And here's a quick result before we actually talk about the results, looking at naturalized flow. So what the river looked like before the series of withdrawals, diversions, et cetera, that we got a good viewpoint earlier about. So at Fort Quitman, it's kind of a washed out slide. I apologize. That white line that passes the Rio Grande here is Fort Quitman. There, the river has undergone a 95% reduction in flow relative to how the flow used to be. So I'm going to leave you all with a couple questions, and I'm not going to answer these questions. I think we just now started asking these questions, and we don't have the answers yet, but I think it's important to continue thinking about these questions moving forward, just from these, I guess I would call them keywords. The stream flow originates from snowpack. From a small area in the basin, water is over-allocated, it goes dry, and you've seen 95% reduction in flow in Fort Quitman, Texas. Is it sustainable moving forward, number one? Number two, what's going to happen if the landscape continues to change and the climate continues to change? We're briefly going to touch on this changing climate here. And the third one are these small headwater regions, the San Juan Mountains, the San Gabriel Cristo Mountains, are they secure? And what does that even mean? What does that word secure mean in terms of water resources? So before I get too poetic, I'm going to get into the heart of what we did, Shailene and Adrian and I did. The first bullet point is we calibrated a model for the Upper Rio Grande Basin. This bullet point took about 2 years right here. And specifically, we calibrated the model for a model of naturalized flow. So we removed all the influence of what is actually going on in the river right now in terms of withdrawals, reservoirs, et cetera, compact agreements, because that really kind of, quote, muddies the water. It's really hard to decipher what is going to happen truly with the climate as we move forward to the year 2100 with that kind of in the way. So we calibrated this model for naturalized flow, and we forced that model with future forecasts, potential forecasts going forward to 2100, and 27 different future forecasts. Not one single forecast is going to give the correct answer. They all have different assumptions involved. So we use 3 global climate models, and these are very coarse resolution models of what is more or less happening on a global level for 3 representative concentration pathways. 2.6, that's with a lot of mitigation. 4.5, a decent amount of mitigation, and RCP 8.5, this is kind of formerly known as the business as usual scenario. We no longer think this is really valid anymore because fortunately we've at least been mitigating a little bit of our CO2 inputs. We then combined these data from these 3 GCMs with 3 downscaling methods. So there's that squirrel or whatever that is. These 3 GCMs are very coarse level models, distributing the precipitation and temperature changes to 2100 over the landscape, but it's too coarse to go over such a heterogeneous area as the Rio Grande. So we integrated 3 different downscaling methods from these 3 GCMs. So here's our input data of 27 different potential climate futures to 2100. We then looked at the difference between all of these data on 3 different time periods and historical periods. So very briefly, historical period more or less 1980 to now. Time period more or less now to 2050. Time period 2 more or less 2050 to 2075. And time period 3 more or less 2075 to 2100. So we looked at the difference between what was happening just recently to these future time periods. And before we look at the outputs of this model, let's look at what the model itself gave us, which I think is as impactful, if not more impactful, than what these climate scenarios show us. Come on, clicker. Here we go. So this is what a model of naturalized flow looks like versus what you see on the ground at USGS gauges. I don't know why it's so washed out. I apologize. That these lower lines, they should be gray lines here, are what the gauges are showing through the water year. So the water year from October to October on the x-axis, CFS on the y-axis, and a traditional hydrograph approach here, cumulative hydrograph on the right-hand side from upstream to downstream. So Rio Grande del Norte to Rio Grande Fort Quitman. I apologize, these lines are hard to decipher on the screen, but in general, at the Rio Grande del Norte, we see very little difference between the USGS gauges and this model of naturalized flow, which makes sense because we have minimal withdrawals upstream of as we go downstream, we see significant differences between more or less how the river was and how the river is now. And what we're doing is we're basically chopping off this huge rising arm and falling arm of the hydrograph. This is, most of this is that snowmelt pulse coming from the Sangre de Cristo and the San Juan Mountains. And we are just removing that for storage, compact agreements, et cetera, et cetera. And that difference between the USGS gauge, what we actually see on the ground, and the naturalized flow is attenuated as we go downstream. And at Fort Quitman, Texas, this is where we see that 95% reduction in flow relative to the native state. You can't see many of these gray lines because for some reason the slide isn't showing up, but this gray line is you can barely see it not far away from that 0 line. Here's my favorite picture, Shailene's least favorite picture of the state line USGS gauge, where we have a ravaging 10 CFS going through there. And this is just to show that sometimes this was also normal in naturalized flow regimes, in native regimes as well before withdrawals. You look at these shoulder seasons, you are going to have low flows in a lot of these points as well, regardless of withdrawals, et cetera. Except to reiterate, what we are doing is we are taking that snowmelt pulse that comes down the river for downstream water rights. So here's the calibration, looking at a standard hydrograph approach. You can look at it in terms of instead of a percent difference, an absolute difference between naturalized flow from the model and the USGS gauge. We're at Fort Quitman, Texas, here in green, right here. We see very large differences, upwards of 15,000 CFS difference. where we would see that primary stream, snowmelt pulse, more or less the same up in the headwaters at Del Norte. So now we can integrate this model of naturalized flow, with future forward forecasts of the climate from these GCMs. So this is a little bit complicated. Right here, we have the three RCPs, 2.6, a lot of mitigation, 4.5, a little bit of mitigation, RCP 8.5, no mitigation for the climate, and three time periods now to 2050, time period 2050 to 2075, time period 2075 to 2099, and these are the primary stream flow segments that flow into the main stem of the Rio Grande. And this is looking at an ensemble mean. This is the mean of all those 27 scenarios of what might happen in terms of earlier streamflow timing or later streamflow timing. Streamflow timing, which is when the majority of that snowmelt pulse would historically roll down the river. And the first thing to note is, regardless of time period and regardless of RCP and these key headwater areas in the San Juans, Sangre de Cristos, in red, we see earlier streamflow timing by significantly earlier, greater than 1 month in some places in San Juans and Sangre de Cristos, especially at this RCP 8.5. I believe this is like 43 days off, something like that, just west of Crete, Colorado. But RCP 4.5, the later time period, we have streamflow timing greater than 1 month off. I don't think this would come as a shock to many hydrologists and hydrographers. We know that the climate is warming, so that's not necessarily precipitation changes the timing. What changes the timing is the temperature. Patternization of temperature on the landscape is pretty clear. Universally, we have temperature going up, so we have much earlier streamflow pulse from that snowmelt. That is propagated downstream to Fort Quitman. It's hard to see the colors on here. I apologize. But at Fort Quitman, RCP 4.5, it's a little less than a month early at that latest time period. So I guess I will leave you with one question: is what happens when streamflow timing is disconnected with the primary growing season? Okay, streamflow volume. Streamflow timing was pretty straightforward. We are going to have earlier streamflow timing, regardless of the time period, and RCP. Streamflow volume is not dictated as much by the change in heat over time. It's dictated by precipitation, specifically that pattern of precipitation change over time. This is the ensemble mean of all these 27 different scenarios. And they all have different ideologues of how precipitation is going to be distributed over space. In general, we have slight decreases in Fort Quitman. This is looking at the cumulative hydrograph, so cumulative volume over time. So RCP 4.5, the latest time period, we have a slight reduction in streamflow volume. There are areas where we will actually, according to these climate forecasts, see increases in volume over time. And there's also a good amount of areas where we will see significant decreases potentially in volume coming from the precipitation over time. One of the hot spots, so to speak, or areas of reduced precipitation, unfortunately for us, is Jemez Mountains and the Sangre de Cristo Mountains, where we see fairly uniform decrease according to these models of precipitation, therefore volume. That's not necessarily, according to these scenarios, going to be propagated all the way down to Fort Quitman, because this is just one area. And the headwaters, in fact, they are showing increases in rain events during the snowmelt season. Snow, unfortunately. Snow is like this giant reservoir that we can use that will hold water without us having to do anything. So it's unfortunate that's not going to come as more snow, but more liquid precipitation. The take-home message here, though, is really it's a lot fuzzier when you talk about streamflow volume in terms of streamflow timing. We will see a slight reduction in Fort Quitman according to these, but a lot of these scenarios conflate the result of each other. Some of these GCMs with the downslope method will show significant increases. Others will show significant decreases. With that said, We have a website where we can look at specific global climate models, specific RCPs and time periods in specific subbasins, if you care to get a better picture of what may happen in the future in terms of volume and stream flow timing. This graph is fairly complicated. I've been looking at it for years and still come up with new potential conclusions. So this is a very handy tool to look at if you're interested in. But the conclusion for the volume is this: even if we are potentially seeing small changes in naturalized flow, this could mean huge changes for what we're actually seeing on the ground right now. The river is not a river of naturalized flow, obviously. So if we have a ravaging 10 CFS flowing through here at state line, if we're just 2 CFS off, that could mean big changes for the river in terms of volume. So the take-home message here, the take-home message here is that the river's changing. We know it's changing in terms of how much it's changing. We've tried to quantify it, but it's more complicated than that. The landscaping is also changing at the same time. But projected future changes are primarily from a changing snow regime. This is my current work right here. These changes are currently occurring in primarily small forested watersheds. We know these forested watersheds are changing dramatically. The Rio Grande National Forest, for example, 90% of the spruce forest has already been affected by the spruce beetle, and that directly affects the snow. As such, that affects the downstream snow water resources. This model does not look at landscape change, but we know that is very impactful for the downstream water resources. These forests, to reiterate, are changing rapidly. However, we can be creative if we need to thin the forest. The National Resource Council projected 300 to 700% increase in fire activity for a 1 degree mean increase in mean global temperature. We've already seen that, right? So how could we potentially thin the forest if we have to, in order to optimize at the same time snow water resources for downstream water resources? This is what we're currently working on. We're really excited about that. But getting back on track, which we just talked about, small changes in naturalized flow can lead to large changes in the river's current river state. Stream flow timing may change more than volume in the future, and in fact, that stream flow timing may be greater than 1 month off in this naturalized flow. So yeah, that's all I have for you guys. So happy to take any questions now or here a little bit later.
As a note, we do have a call out to AV to just look into that feedback. Sorry.
What's that?
I did call AV. They're going to look into that. So apologies.
No, you're good. You're good.
Okay. Any questions for Dave?
Dave, thank you for that. While we have you here, could you maybe describe what our new hydrograph is going to look like based on the data that you've presented?
That's a really good question. This is just a model of naturalized flow. We'll see that hydrograph kind of go forward because that pulse is no longer coming down around the 1st of June. It's coming down a lot earlier. But the Bureau of Reclamation is using these climate forecasts, integrating that with a watershed model into the Uruguay model, because it's really hard to say what may actually happen with the river as we know it. So I believe they are working on, I think it's called the Basin study, and they are not done with that right now. So we shall see. That's a really good question, but we know things will have to change if we have a month earlier stream flow timing.
Just if you could go back to that first set of graphs on your naturalized flow. It seemed like on the third one down, kind of the runoff on the gray line sort of came back in a little bit. What's happening there?
Right, Otoe here?
Right there, that's Otoe. I couldn't see.
Mm-hmm.
Yeah. You know, the gray line kind of on the second, third, and fifth goes away more or less, but that Otoe one, there's still a little bit of a gray.
So you'll notice we started at the Rio Grande, this Colorado state line. Oh, sorry about that. So you'll notice we started at the Colorado state line. Once you get to the Colorado state line, they take as much water and that graph goes down. But once you get past the state line into New Mexico, then we have that inflow from the Crystal Mountain that kind of starts to replenish, the stream flow a little bit. It's still not, very much That's what you're seeing.
The sun grid's input, okay.
Any other questions?
You were talking about how the changes in the forest composition would affect things, and you mentioned fires. Are there, how else do changes of the forest affect like hydrology or the snowpack or anything like that?
Well, I guess I was alluding to silvicultural practices there, but whether it's the bark beetle, a forest fire, silvicultural practices, you could see increases and or decreases in snow water resources, therefore downstream runoff, depending on how that fire or the bark beetle, the silvicultural practice, created different prioritization of the forest on the ground. It's basically a competition between shading from the forest, newfound shading, as well as increased radiative forcing against those forest trees. The trees are these giant rods going into the atmosphere, and they can be 40 degrees C warmer than the mean ambient temperature. It's crazy how much heat can be generated from those trees. So they can also act to melt a lot of that snow, but also shade the snow. So you can kind of optimize the shading and try to decrease the radiative forcing, that long wave radiation in the forest.
Anybody else?
So I was curious when you talked about the volume, did you look at like at Fort Quitman, you said it was nearly just a small decrease. Like, is there a stronger decrease at the state line or at Otoe specifically? And do we gain that below Otoe or not?
I believe I misspoke. As we go down into the watershed in general, Fort Quitman shows the greatest decreases from what we see today from naturalized flow. That's where we have that 95% reduction. A lot of that is due to the canal next to it, but also primarily because of compact, et cetera, et cetera. Yeah. Does that answer your question? What?
I guess I was wondering, I know you're looking more at Streamflow, but if we get maybe, I don't know, I mean, I've heard that we might, with climate change, get about the same amount of precipitation, it just falls differently. So I was curious, like, well, if we get less snowpack, will we get more rainfall? And if it falls below Otoe, does that help New Mexico or not? Because if we get more volume that's below Otoe, we don't necessarily have to account for that.
So the change in streamflow volume, this was looking at cumulative volume throughout the year. If you parse what we're basically looking at individual hydrographs for each of these segments, if you parse this into kind of a snowmelt signal and more of a monsoonal signal in the south, in the more southern areas, you see slight decreases in that monsoon signal moving forward. So continued decrease in that area. But as we know, that system, at least in this naturalized regime, is 100% propagated by all the water generated up in that universe.
Anybody else have a question?
Yeah, one question. You were referring to the volume component of your model. Is that sensitive to temperature increases and evaporative demand?
Also very sensitive to that. It would not be as sensitive as the river as it is today when you're holding these waters in reservoirs where you're going to get even more increased evaporative potential. But we also would see increases in sublimation, water loss from snow, from increasing temperature as well. But in general, volume is more or less dictated by precipitation, and the timing is more or less dictated by the temperature. Excuse me.
Did you all hear that in the back? Okay. Any other questions? Thank you so much, Dave.
All right. Thank you all.
So we are now ahead of schedule. Unfortunately, lunch